All right, so the last part of the chapter that we're going to cover is all about solutions. So let's first define what a solution is. A solution is a homogeneous mixture. What does it mean when I say homogeneous? It means evenly mixed, or the same throughout, right? Versus heterogeneous, which means it's different throughout, not mixed evenly. So it's a homogeneous mixture of two or more substances. One of which is a liquid. All right, so let's kind of define this using a mathematical formula. So the first thing we have is a solvent. That's the liquid component. So the thing doing the dissolving. And then the thing being dissolved is called the solute. This is the thing being dissolved. And this is like a nature soundscape out there. All right. So you can have more than one solute. So for example, if you're in the hospital and you're getting an IV bag, chances are there's a bunch of different things dissolved in that water solution, right? However, the key thing is you've got a liquid dissolving some solute or multiple solutes. All right, the next term we have to define is concentration. Concentration is a pretty simple concept. It's how much solute is dissolved in a solvent. More specifically, it's how much solute is dissolved in a given amount of solution. Move this up. All right, this is a pretty generic term, so how are we going to define how much solute is in some sort of volume of solution? Chemists and biologists tend to prefer something called molarity. And that's a quantitative measure of concentration, and I'll just abbreviate concentration, used in chemistry and biology. But it's pretty convenient. So let's define what it is in mathematical terms. And the symbol used for molarity is capital M, not lowercase m. That means something entirely different. And this is equal to the moles of solute, meaning the thing being dissolved, divided by the liters of solution. So the total volume of your solution, or 1 liter. All right. So pretty generic calculation, but let's see it in practice. So we'll do an example problem. All right, in this example, we're determining the molarity. So what is the molarity of a solution when 2.33 moles of sodium chloride are dissolved to make 3.77 liters of solution. So let's do this really quick with our calculators and make sure that your answer has the appropriate number of sig figs. I saw on the last pod that people kind of forgot about sig fig rules. And if you think you got it, give me a thumbs up. All right, show of thumbs, who thinks they got it? All right, so let's try this. First thing we need to do is we need to divide the moles of NaCl divided by the liters of solution. And I gave you the moles of NaCl, which was 2.33 moles, divided by 3.77 liters of solution, which comes out to 0.618. And the units, if you remember, are going to be molarity, so capital M would be your final answer with the appropriate units. Is that what everyone got? Perfect. Key thing to remember, sig figs. People forget about that a lot, but it helps with error propagation and knowing what digits matter and which ones don't. All right, so let's do a harder one. This one's going to require more work, and you may want to work with a partner on it. All right, so the next one is calculate the molarity when 7.66 grams of CaCl2, what's that called? Calcium chloride, right? It's not a transition metal, so we don't need a Roman numeral, but it is ionic, so we do need to omit prefixes. So it's calcium chloride, so we've got 7.66 grams. Let me move this up. And they're dissolved to make 345 milliliters of solution. So I'll give you some time to work on this, but you might need to do some unit conversions as well. Anybody need more time? A few people? All right. So I will give you a hint. Can we just plug in the grams unit? What do we need to do first? Yeah, convert that to moles. What do we need to know in order to convert grams to moles? Molar mass, absolutely. And then the last part is we need to convert the volume from milliliters to liters, so you may need to do a unit conversion there as well. So we can't just plug in 345 in the bottom. So let me do this in two parts. So we've got 7.66 grams, and eventually we need to get to moles. And then we'll do find liters of solution. All right, so let's do the first one together. We'll find the moles of solute. So we've got 7.66 grams. We need to find the molar mass. So let's break that apart. And I'm just going to cheat and draw this over here. We've got one calcium atom. That weighs what? Should be about 40. Specifically, it would be 40.078. Plus our two chlorine atoms, which are 35.453. That gives me a molar mass, let me zoom out even more, of about 110.984 grams per mole. All right, so now we've got our molar mass conversion. We want to cancel out grams. So I put down grams of calcium chloride on the bottom. We want moles. So I'll put that on top. And does the 110.984 go on top or bottom? It would go on the bottom, right? It needs to be paired with the grams unit. 4 grams for every 1 mole. So now we can cancel out grams and grams. And when we go ahead and plug this into our calculator, I'm getting 0.0, whoops, that's not a 0, 0.0690 moles of calcium chloride. I did keep sig figs in here, however, sig figs don't really matter until the very, very final answer, so that's something to keep in mind. All right, and then next we need to find our liters of solution, right? So we know we've got 345 milliliters, and we need to cancel out milliliters and get to liters, and if you remember, 1 milliliter is equal to how many liters? What does the milli unit stand for? Oh, close, 10 to the negative 3, right? So we could plug this in and we could say 1 milliliter is 10 to the negative 3 liters. So I'd say 1 milliliter, 10 to the negative 3, it goes on top. That allows us to cancel out milliliters. Milliliters, we're left with liters as our final unit. This is 0.345 liters. All right, so now we've got the 2 important pieces. We can do our final calculation. So let's plug this in. Molarity equals moles over liters, which we said was 0.0690 moles divided by 0.345 liters, which gives us a final answer of 0.200 molar. So this would be our ultimate final answer. And if you noticed, I was very careful to only use 3 sig figs here. So sig figs are really important with stoichiometry, just as they are with any sort of measured values in general. Does that make sense? The number one mistake students make with solutions is they forget to convert grams to moles, or they convert their volume to an incorrect unit rather than liters. All right, so let's do a bit of review, and then we'll jump into the carbonates lab. So I've got a handful of sample questions. So let's start with this one. Which of the following is not a properly balanced equation, and how would you write it correctly? So I'll give you a minute to think about this and talk with your neighbor and see if you agree. First of all, let's identify the one that's not balanced. If we look at the first one, I'm seeing 4 phosphorus on the left. I'm seeing 4 on the right. That looks good. 12 chlorines, so it looks to me like A is okay. If we look at B, I've got 2 nitrogens on the left, 2 on the right, 2 oxygens on the left. Oh, only 1 on the right. So it looks like B is not correct, but let's go and double check C and D. So C, we've got 1 calcium on each side. How many oxygens do we have on each side? 2, right? So the 2 outside of the parentheses indicates we have 2 hydroxide units, each of which have 1 oxygen. So that's 2 total on the left. And then we've got 2 waters, each with 1 oxygen on the right, so 2 oxygens on each side. Hydrogens, similar idea. We've got 2 from the hydroxides, 2 from the HBr, so that's 4 total, and then 4 total from the water. And then 2 bromines from HBr and 2 bromines from calcium bromide. And then last but not least on the bottom, got 3 carbons on each side, so that looks good. Got 8 hydrogens on each side, that looks good. And then we've got 10 oxygens on each side. So how would we balance B correctly? We've got to put in some sort of coefficient in front of at least one of these spots. Yeah, so let's try that. So you recommended putting a 2 in front of our dinitrogen plus our oxygen, and then you said put a 2 in front of the N2O. And what is N2O, just so we can name it? Dinitrogen monoxide, according to our naming system. All right, so now we've got 4 nitrogens on the left, we've got 4 nitrogens on the right, we've got 2 oxygens on the left, and we've got 2 oxygens on the right. So this looks good to me. We properly balanced it. So make sure you are comfortable balancing equations. It does take a while to get good at, and I posted more practice problems. All right, any questions on this? No? All right. This one's a little abstract. How many carbon atoms are in one formula unit of this compound? Yeah, so let's take a look at this. I would check with your neighbor and see if you agree. This is a tricky one that people get confused with. Everybody thinks 7? That's good. All right, so let's check this one. So first thing I see is we've got 3 carbons times 2. So this whole unit would be 3 times 2 plus this one over here. So we've got 6 plus 1 equals 7 total carbons in that formula unit. So make sure you do check all of the carbons. Sometimes carbons might be in a parentheses unit, and sometimes it might be outside. You have to add them all together.
What is that?
I'm honestly not sure. It's always hard, so whenever you see something written out as a formula unit like this, you don't really know much about the connectivity, so how the atoms are arranged in space, and it's kind of hard to know. All right, what is the mass in grams of 2.5 moles of ammonia, NH3? So you might need paper for this one. So before we do this problem, what do we need to know? Does anybody want to help me out? We've got to have some sort of conversion. Yeah, the molar mass, right? So if we think about this, we need to find the molar mass of ammonia. We've got 1 nitrogen atom, which is 14.01, plus 3 hydrogens. Oops, I'm drawing a hydrogen. And the hydrogens are about 1.01. Gives me a molar mass of about 17.03. Okay, so that's a really important unit conversion we need to do. So we've got 2.5 moles of ammonia. We want to cancel out moles of ammonia. And we want to go to grams of ammonia. So does that 17.03 go on top or go on bottom? Top, right? It gets paired with the grams unit. So now we can cancel out moles of ammonia. We're left with grams of ammonia. And at least from my calculator, I'm getting 42.5. Which looks like that corresponds to answer B, right? I did notice on the last pod that I handed back that a lot of people were having calculator errors. So if you are struggling to put stuff into your calculator, you've got a few options. One is, out of an abundance of precaution, use as many parentheses as possible. Or 2, if you're still struggling on how to do that, either stop by my office or the MARC and make sure that you're putting it in correctly. I always feel bad when people have their problem set up correctly, but they're just not typing it into their calculator right. All right, let's do a few more. There we go. So consider the combustion of propane as represented in this chemical equation. When 7.5 moles of oxygen are consumed, how many moles of CO2 are formed? I will give you a hint while you're going through this. The coefficients matter a lot for this problem. So those numbers that come before tells you the ratio of reagents and products for this reaction. Anybody need more time on this one? All right, so let's try this. We've got 7.5 moles of oxygen. We want to cancel out moles of oxygen, so I'll put that on bottom. And instead, we're trying to figure out moles of CO2 formed. So we'll put moles of CO2 on the top. What's the ratio of CO2 to oxygen in this reaction? Looks like we have 3 moles of CO2 for every 5 moles of oxygen consumed, so it's a 3:5 ratio. And if we plug this in, I'm getting 4.5 moles of CO2. So we can go ahead and circle C as our correct answer there. Make sense? So the coefficient basically tells you the ratio of one molecule to another molecule in your balanced reaction, and so you can use it to convert moles of one reagent or product to moles of something else, as long as you're starting out with the balanced equation. These are a little tricky. Let's do one more, and then we'll do more stoichiometry practice. We'll basically spend the rest of the week doing stoichiometry practice and exam review. All right, a solution is prepared by dissolving 0.50 moles of solute in 250 milliliters of solution. If you remember, molarity is moles over liters. We're given the moles, right? But we're not given liters, we're given milliliters. So first thing I would do is convert milliliters to liters. And we saw before that 1 milliliter is equal to 10 to the negative 3 liters. So then we can cancel out milliliters, milliliters, get left with liters. So this is the same as 0.250 liters. So now we can say, all right, we've got 0.50 moles divided by 0.250 liters, and that gives me a final answer of 2.0 molar. So it looks like the correct answer for this one would be E. So make sure that you do always convert your volume to liters when you're doing solution problems. All right, so what I want you to do now is to grab your carbonates handout and then get with your lab partner. And what I'm going to do is I'm going to help you with the first problem. And then once you have that first problem figured out, it should be pretty intuitive to figure out the last 2. But if you are stuck, you're more than welcome to stop by my office or email me and ask me for help. So let's pull out the carbonates one. All right, the first part, 1A, says describe the product in a complete sentence. That basically just means what did it look like? Was it a white powder? Was it a black powder? Was it clear? Was it colorless? Describe what was going on there. And then B says write a balanced equation for this reaction. Be sure to include phases. We haven't really gone over phases much in class, but it's pretty intuitive. What does S stand for? Solid. What does AQ stand for? Aqueous. That means it's a solution of hydrochloric acid. CO2 is a gas, so we have a G behind it. H2O is a liquid, so we put an L behind it. And sodium chloride is aqueous because it was dissolved in water. So the first thing I would do is double check that this equation is balanced. If this equation is not balanced, none of your other answers might be right. So you have to start out with a balanced equation. All right? And then for part C, it says calculate how many moles of sodium hydrogen carbonate you placed in the beaker. So what you'll do is plug in the amount you put into your beaker. You'll have to find out the molar mass, which is that little X unit here, so I'll let you do that, and then you'll find out the moles of sodium bicarbonate that you had. Then once you find that, you're going to convert from moles of bicarbonate to moles of sodium chloride. So where do these two numbers come from? The X and the Y. What was that? Yeah, the coefficients from the balanced reaction. So you need coefficients for the next part. That'll give you moles of sodium chloride. Then once you have moles of sodium chloride figured out, you're going to use that in part E. And we want to find grams of sodium chloride, so you might need to find the molar mass of sodium chloride, figure out grams. And then part F is the last step where it says, all right, take the mass you recovered from the experiment, divide it from the mass you should have gotten, which you calculated in part E, and multiply it by 100. That's your percent yield for this reaction. What should it be for F? Ideally, it should be 100%, right? You shouldn't be able to create or destroy matter. If you're getting an amount that is way, way off base, what do you think the problem is? It could be a few problems, actually. One could be maybe you misweighed something in the experiment, or two, maybe you just messed up a calculation somewhere. So always double check that this is at least close to 100%. If it's not dead on 100%, that's okay, but it should be in the high 90s. All right, so I'll give you some time to work on this. The subsequent pages are really, really similar. Where instead of starting with sodium bicarbonate, you're going to start out with some other carbonate, and then you're going to react with HCl. You're going to produce CO2, water, and some sort of salt out of the reaction. So I'll give you some time to work on this with your partner and then float around the room to see if you need help.